One of my very favorite topics in science, and in physics in particular, is relativity. And it's my belief that you can understand a whole lot of things about science without necessarily needing to delve into complicated equations, as long as we can find ways of conveying ideas in a way that is visually intuitive. To do that, what I want to talk about today is a way of understanding special relativity using space-time diagrams. And I'll say a few words about the details and why this graph paper looks so funny in a minute. But the basic idea of a space-time diagram is really simple. Time goes upward along this axis. Space goes to the right, or left and right, along the horizontal axis. This is a little backward from what you'll often see in a math class or in a lot of physics graphs where you've got time horizontally and position vertically. But this is traditional in relativity. Particle physicists sometimes reverse these two as well. But traditional relativity, position is left and right, time progresses upward. And if I wanted to draw a diagram showing the relative motion of Alice and Zach, two different observers who are moving relative to one another, I can say that this diagram is from Alice's reference frame. In this diagram, Alice is the person sitting still at position x equals 0 from time 0, 1 year, 2 years, 3 years, 4 years, 5 years, and so on into the distance. We're measuring time in years because for relativistic things, maybe light years and years are reasonable units. We'll talk more about that in a second. And then we're measuring position horizontally along the way. So Alice stays at the same position for all time. She's just going straight up. Zach is moving at 2/3 the speed of light. Light moves, by definition, at 1 light year per year. So light, 1 light year per year, would go at a 45-degree angle up here. It's no coincidence that's where all these curved lines are asymptoting to. But Zach is moving 2/3 the speed of light, 2/3 light years per year. So the simple thing you do with space-time diagrams, again, ignore the curving lines for the moment. You can do this on any graph paper. The simple thing you do is just say, I'm going to assume that Zach and Alice pass each other at time equals 0 and position equals 0. That's our usual reference point at the origin of coordinates, Alice's coordinates in this case. I'm going to assume they pass each other there, and I'm going to draw a line with slope 2/3. Slope 3/2. 2 light years. If he starts here at the origin, Zach is going to move 2 light years for every 3 years. 2 more for every 3, 2 more for every 3, 2 more for... You get the idea. 2 light years for every 3 years. So I'm going to go ahead and draw a line, make sure it goes through x equals 8 light years at time equals 12 years. And make sure it goes through the origin, because I'm starting there. I'll draw this line. Once I'm all set to draw the line, I'll just draw out the whole length of this thing. And there we go. So I've drawn a line on here. I know there are a lot of lines going on, but hopefully you can see the one line that's different than all the others, the straight line going along here at speed 2/3 the speed of light, 2/3 light years per year. That is the path that Zach takes. And you'll find if I had chosen a speed of 1/10 light year per year, I would have gone one light year this way and 10 years that way. My angle would have been like this. If I had gone 9/10 the speed of light, 9/10 light years per year, I would have gone over like this. Always starting at the origin. You'll notice the slower I go, the steeper my line is on the graph. The faster I go, the flatter my line is on the graph. And in relativity, you probably know that the speed of light, c, is the fastest possible speed that a physical object can go. And that means the speed of light, as I mentioned down here, 1 light year per year, is always going to be a 45-degree line on this diagram. So the faster you go, you're never going to be able to go faster than a line that's going to be 45 degrees on this diagram. The faster you go, the more you tilt down toward 45 degrees. Okay, so that's the basic idea of a space-time diagram. And you can do that all the time. The beauty of this special graph paper with these curves on it is that it's going to capture a lot of the mathematics of relativity for you without you having to use equations. This particular video, I'm going to just be explaining the concepts behind it, so I am going to use a few equations. but I want you to understand that you don't need equations to use. Once you have this hyperbola graph paper, you can use that for a lot of the things you would want to do in relativity. Let me explain. Every observer in relativity experiences time differently. That's one of the fundamental facts about relativity. Every observer experiences space differently. That's another fundamental fact. But what everyone can agree on is the space-time interval. This is fundamental to the structure of space and time as seen in relativity. And it's given by this delta S is the space-time interval, and it's given by this metric equation. It's given by this equation saying if you take the time between two events, remember an event in relativity is something that happens at a particular time in a particular place. So it's a point, like the origin here, where Zach passes Alice, is an event in space and time. That's an event. Or when 10 years have passed from Alice's perspective, that particular point on this line is another event in space and time. So you measure the delta t, the difference in time between two events is seen by one observer, and then the same observer measures the delta x, the difference in space between two events. If you do delta t squared minus delta x squared over c squared, the factor of the speed of light is there to get the units the same. This will all be in years squared, time squared. If you do this subtraction, the beauty of relativity is every observer will get the same delta S. That's one of the fundamental pieces of the structure of space-time in relativity. And this is where this funny hyperbola graph paper comes in, because this equation, t squared minus x squared, looks a heck of equals some constant that everyone agrees on squared, is a heck of a lot like the standard equation for a hyperbola, one of the conic sections, in ordinary algebra. Y squared minus x squared equals a constant. If the constant's positive, you're going to get hyperbolas that bend upward. If the constant's negative, you're going to get hyperbolas that bend sort of sideways. And what I've done over here, this graph paper, by the way, was inspired by and taken from some paper available by my colleague Tom Moore at Pomona College. This graph paper has done these hyperbola calculations for you. If I had y squared minus x squared equals 1, for example, well, y equals 1, x equals 0 works, but there are a lot of other points that work as well. And so what this has done, I guess I'm doing delta t squared minus delta x over c squared. What I've done is say every point that has a delta s of 1, or a delta s squared of positive 1, is along this hyperbola that passes through time equals 1, x equals 0 right here. Every hyperbola, or every point that has a delta s squared equals 2 squared is somewhere along this hyperbola. If you've got a delta s of 4, that'll be along this hyperbola somewhere. So, for that matter, if you have a delta s squared of negative 4, remember negative numbers out in front in that equation will correspond to hyperbolas going this way instead. A delta s squared of negative 4, you'll be somewhere along this hyperbola. Okay, that's the idea of what this graph paper is doing. And what we're going to see is that this principle that all observers agree on the delta s squared, combined with these hyperbolas, allows us to do all sorts of calculations in relativity without needing to refer back to equations ourselves. So let's look at this one. I've got Zach's path here going at 2/3 the speed of light, 2/3 c, up through this graph. That's Zach's path. So I'm going to ask the question, when Alice believes that Zach has been gone, after having passed by here at time equals 0, gone for 10 years, how much time has passed for Zach? Well, okay, so first of all, I need to identify that event as seen by Alice. That event, time equals 10 years. Remember, this graph is based on Alice's coordinates, and so every event that she thinks happens at time equals 10 years after Zach passed by, every one of those events will be along this horizontal line. Well, here's the point where Zach is living on that horizontal line. So I will put a little star there just to label that is the event we're talking about. When Alice thinks that Zach has been gone for 10 years, how much time has passed for him? Well, first let's do it the calculation way using the space-time interval. I know that the time that has passed is 10 years, so delta t, oh, well, let's see, I don't need to recopy that down. My delta t squared is 10 years squared minus 1 year per light year is 1 over c, times my delta x. What is my delta x here? Well, you can see on the graph, following it down, it's about 6 2/3. Actually, 2/3 times 10 is 2/3 times 10 is 20/3, or 6 2/3 exactly. So this is times 6 2/3 light years squared. You can see the units work out. Light years cancel out, and I've got years in there. So 10 squared minus 6 2/3 squared. You can go through and calculate this out. I'm not going to do it in fractions. I used a calculator. I get approximately, I guess, 7.454 years quantity squared. That's what I come up with when I do this. So it's about 7.5 years going through this. So I can do that, and that means, okay, this is my delta S squared, right? That's my delta S squared for this calculation. Well, here's the trick. As seen by Zach has a different perception. Zach's measurement, Zach is moving at a constant velocity, and one of the fundamental ideas in relativity is if you're moving at constant velocity, you feel like you're sitting still. Zach's reference frame is just as valid as Alice's. Zach, in his own reference frame, will believe that he is sitting still, and therefore Zach says, I've been at x equals 0 this whole time. Zach says that this delta S squared is equal to some unknown delta T Zach squared. The subscript z is just to say this is Zach's measurement of time, minus 1 year per light year times how far does Zach think that Zach has moved? Not at all. He thinks he's sitting still. So 0 light years. In other words, from Zach's point of view, Zach is just sitting still. So delta S equals delta T Zach. And that tells me that Zach thinks that 7.5 years have passed, 7.45 years have passed since he passed by Alice at the origin. Zach says that it's 7.5 years between these events, where Alice says that it's 10 years between these events. Okay, that was all done with equations. We could have done this with a Lorentz factor, the gamma as well, but this is all done with equations. We can do the space-time interval. That's a good way of thinking about it. Here's where the space-time diagrams are beautiful. This event, if you're following along someone's own path, we know that Zach has delta x equals 0, so his interval is his time. We just argued that down here. Zach's interval is his time. That means if we just look at what the delta S is along this path, that it tells us Zach's experience of time. Where does that take me here? Well, let's look at it. This star, this event, is somewhere almost exactly in between these two curving hyperbolas. Almost exactly. And if I trace them back, one of them is the 7-year hyperbola, and the other is the 8-year hyperbola. So since this event is halfway between the two, that means the delta S there is about 7.5. I would not be able to read this to 4 sig figs of accuracy on this sheet, but I could read it to 2 sig figs pretty easily. 7.5 is awfully darn close to what I might have said 7.4, but it's awfully darn close to what I would have estimated looking between these points. That means that, hey, I can just read off Zach's time directly from the diagram without any additional fancy calculations, without any math required. I can just read it off. The two ways of doing it are, I guess the easiest way to think about it is I'm just going to figure out where that is between these hyperbolas and extrapolate back where would your hyperbola come and hit on the y-axis, on the time axis, and assign that as my time, 7.5 years. So that's the beginnings of how we do these things. Another way to think about it is to say Zach thinks that 1 year has passed every time his path crosses a hyperbola. So let's count those. Here's 1 year, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years. Up here would be 8 years, and that is very close again to being halfway between the 7 and the 8 year marks. So I can find the time that Zach has experienced by just counting his years along this line and figuring out where that goes. Okay, that's the basics of how you use hyperbola graph paper to do relativity via space-time diagrams without equations. And I think that's probably a good place to stop this little introduction. I'll say another word in a second in a separate video about how to think about Zach's own perception of time. But for now, we'll stick with this. We've talked about how to use this graph paper to do calculations in relativity just by reading off of a graph rather than anything fancier than that. And I think this is a powerful thing and can help people understand relativity even if they aren't fond of algebra.